So, we are given a system of equations, namely 3 equations in 3 unknowns. We observe the following from this system. A is a diagonally dominant matrix. The matrix A is a diagonally dominant matrix and it has the property that modulus of aii is greater than sigma j is equal to 1 to n, j not equal to I modulus of aij for all values of I which run between 1 and n. Say for example, if I take I as 1, then mod a11 is greater than sigma j is equal to 1 to n modulus of a1j. So, j should not take the value 1. So, what is it? It is modulus of a12 plus modulus of a13. So, namely the coefficient of x1 which is a11 in absolute value is bigger than the sum of the absolute values of the coefficients which appear in the same equation. So, that happens for I is equal to 1, that should happen for I equal to 2, I equal to 3 and so on. If this property is satisfied for a matrix A, then we say that the matrix A is a diagonally dominant matrix. If you are given a system of equations with the coefficient matrix as a diagonally dominant matrix, then we have a result which says that if A is a diagonally dominant matrix in the system Ax is equal to B, then Gauss-Jacobi method and Gauss-Seidel method converge to the solution for any arbitrary starting vector for the unknowns x. And here we are given a system such that the coefficient matrix is a diagonally dominant matrix. So, we can start with any arbitrary initial vector x naught, which is x1 naught, x2 naught, x2 naught, and apply either Gauss-Jacobi method or Gauss-Seidel method, then our successive iterates are guaranteed to converge to the solution of the system. So, we first write down the result and then work out the solution for this problem. So, the result says, and it is given by the following theorem, and it states that if A is a diagonally dominant matrix, then Gauss-Jacobi method and Gauss-Seidel method converge for any arbitrary starting vector to the solution of the system. Ax is equal to B. So, the theorem guarantees that the sequence of iterates generated by Gauss-Jacobi method and Gauss-Seidel method for this problem will converge to the solution of the system Ax is equal to B. So, let us first write down these methods. What should we do? I must associate the first equation with the first unknown, and therefore, x1 should be solved from the first equation, and that gives you 1 by 10 into 9 minus 2x2 minus x3. x2 is 1 by 10 again minus 22 minus x1 plus x3. Thirdly, the x3 is 1 by 10 into 22 plus 2x1 minus 3x2. So, having written out this step. If I want to apply Gauss-Jacobi method, my solution at the kth step for x1 will be obtained by using the solution for k minus 1th step for x2 and the solution for x3 at the k minus 1th step. The solution for x1 at the kth step will be obtained by using the values at the k minus 1th step for x2 and x3. Similarly, x2k will be given by 1 by 10 minus 22 minus x1 at the k minus 1th step plus x3 at the k minus 1th step, and x3k is 1 by 10 into 22 plus 2 times x1 at the k minus 1th step plus x2 at the k minus 1th step, and that is for Gauss-Jacobi method. What is it for Gauss-Seidel method? So, let us write out the details. This will be the iterative procedure that I will use when I make use of Gauss-Seidel method to generate the successive iterates. So, we shall present the solutions for both these methods and see how the solutions look like. So, the solutions using Gauss-Jacobi method and Gauss-Seidel method are presented here. We start with an initial approximation for x1, x2, x3 as 0 and apply Gauss-Jacobi method every time using the previously available values for the variables are used and the values at this step are computed. When we perform our computations, we see that at the end of 7th iteration, we notice that the solution obtained at the 6th iteration and the 7th iteration are the same for all the 3 variables. So, I stop my computations and take the solution as x1 equal to 1, x2 equal to minus 2 and x3 equal to 3. Now, I perform the solution using Gauss-Seidel method. In this case, the solution at any step is computed using the currently available values for the variables at that particular step. So, when I do that, the solutions are given in this table. I again start with an initial vector 0 for all the 3 unknowns x1, x2, x3, and I perform 5 iterations and I observe that the solution turns out to be 1, minus 2 and 3 at the end of 5 iterations for x1, x2, x3 respectively. So, the sequence of iterates generated by Gauss-Seidel method converge faster than the sequence of iterates generated by Gauss-Jacobi method. The question now is, will the sequence of iterates generated by both these methods will always converge to the root of the equation? So, let us look at some examples and give an answer to this question. Let us consider the following example. The system is given by x1 minus x2 minus 2 x3 equal to minus 5, x1 plus 2 x2 plus x3 equal to 7 and x1 plus 3 x2 minus x3 equal to 2. We see that the system is not diagonally dominant. And therefore, there is no guarantee that the scheme will converge. The theorem that we stated said, if A is a diagonally dominant matrix, then the sequence of iterates generated by Gauss-Seidel method and Gauss-Jacobi method will converge to the solution of the system Ax is equal to b for any starting initial vector. So, the conditions are sufficient and not necessary, and therefore, in this case the matrix A, which is the coefficient matrix, is not diagonally dominant, and therefore, there is no guarantee that the scheme will converge. At the same time, we cannot say that both the schemes will diverge. So, let us work out the details and see what we get, starting with some initial vector. So, if I start with an initial vector x1 0, x2 0, x3 0 equal to 0, then if I apply Gauss-Jacobi method, that gives me at the end of 10 iterations the solution for x1 as 302.125 and x2 is minus 106.188 and x3 at the 10th iteration turns out to be 217.375. x3 at the 10th iteration is 217.375. These are the values of x1, x2, x3 at the end of 10 iterations. Let us work out the same problem using Gauss-Seidel method, and in this case at the end of 10 iterations we see that the solution for x1 is 85,011.3 and that for x2 is minus 58,568.9 and that for x3 is minus 90,697.4. So, both these methods diverge from the true solution. Let us now consider another example. Suppose say the system is 4x1 minus 2x2 plus x3 is 12, 2x1 plus 3x2 minus x3 is 7 and 2x1 minus 2x2 plus 2x3 is 8. So, let us look at the system. So, the system is not strictly diagonally dominant. So, let us now try to work out starting from some initial vector and using Gauss-Jacobi method and Seidel method. So, again I start with the initial vector x1 0, x2 0, x3 0 to be 0. Then Gauss-Jacobi method gives me at the end of 18 iterations the solution to be x1 18 is 3, x2 18 is 1 and x3 at the 18th iteration is 2. And Gauss-Seidel method also gives me the solution at the end of 15 iterations for x1, x2, x3 as 3, 1 and 2. So, we say that the Gauss-Seidel method and Gauss-Jacobi method converge for this problem, because in this case the exact solution for the problem is x1 is equal to 3, x2 is equal to 1 and x3 is equal to 2. So, just see Gauss-Jacobi method and Gauss-Seidel method both have converged to the exact solution. So, they generate sequence of iterates which converge to the exact solution of the problem, and we observed that the matrix A is not a strictly diagonally dominant matrix. So, the conditions given in the theorem are sufficient and not necessary. So, what is it that we infer from the result of the theorem and from the examples that we have taken? Given a system Ax is equal to b, if the coefficient matrix A is strictly diagonally dominant, then the sequence of iterates generated by both the methods will converge to the solution of the system Ax is equal to b starting with any initial vector. If the, on the other hand, given a matrix A such that it need not be a diagonally dominant matrix, the sequence of iterates generated by this matrix may either converge or diverge. So, the conditions given in the theorem are sufficient but not necessary. So, when we are asked to solve a system of equations, we check whether the given system is such that it has its coefficient matrix to be a diagonally dominant matrix. If suppose some exchange of equations can be made such that the coefficient matrix can be changed into a diagonally dominant matrix, then you can apply both the methods and generate a sequence of iterates which will converge to the solution of the system of equations. If the matrix A that you are given is not strictly diagonally dominant, then nothing can be said when you apply your methods such as Gauss-Jacobi method or Gauss-Seidel method, because the sequence of iterates may either converge or diverge for any initial starting vector. So, this completes our discussion on the iterative methods for solving the system of equations. So, let us quickly summarize what we have done in this section on solution of algebraic system of equations. So, we said that using elementary operations, we can convert a given matrix A to an upper triangular matrix, and when we convert it into an upper triangular matrix, then back substitution method will enable us to solve the system immediately. So, this was used when we described Gauss elimination method. Then we said that we may have to divide a particular equation by a very small quantity when we apply Gauss elimination method, in which case the round of errors will become very large. In order to avoid that, as well as to avoid the situation where we may have to divide by a quantity which is the pivot and the pivot turns out to be 0 at that particular step, then in such cases the partial pivoting technique must be used in Gauss elimination method, so that we can solve, we can avoid division by 0 or division by a small quantity, and the solution can be obtained. So, summarizing the methods for solving a system of equations, we said that we have two classes of methods, namely the direct methods and the iterative methods, and the direct methods comprise of decomposition methods, Gauss elimination method and Gauss-Jordan method, whereas the iterative methods that we have learnt in this course are Gauss-Jacobi method and Gauss-Seidel method. So, given a system of equations, we can apply any one of these techniques depending upon and obtain the solution of the equation, and in all the cases, in both the cases, we have a way to improve our solution, namely we can perform the iterative improvement method in the case of direct methods to get our solution to be as accurate as is required, and in the case of iterative methods we can perform the iterations as many times as it is required. The solution is obtained correct to the desired degree of accuracy. So, we close this section on the solution of a system of algebraic equations and move on to the computation of eigenvalues and eigenvectors of a given matrix A. We consider matrix eigenvalue problems. So, we are given a matrix A which is an n cross n matrix. And let lambda be a scalar. Our goal is to solve an equation of the form Ax is equal to lambda x. We seek a non-zero vector x and a scalar lambda which satisfies this equation Ax is equal to lambda x. The scalar lambda is called an eigenvalue of the matrix A, and the non-zero vector x which is associated with this eigenvalue lambda is called an eigenvector of the matrix associated with the eigenvalue lambda. So, solving this equation is equivalent to solving an equation of the form A minus lambda I into x is equal to 0, which is a system of homogeneous algebraic equations. So, the condition for non-trivial solution of this system, let me call this S star, of star is equivalent to requiring that the determinant of the coefficient matrix, namely A minus lambda I, is equal to 0. So, if you find determinant of A minus lambda I and equate it to 0, you will observe that you have an nth degree polynomial int lambda whose roots are the eigenvalues of the given matrix A. And once you determine these eigenvalues, you substitute each of those eigenvalues here and then solve the system A minus lambda I into x is equal to 0, and you look for a non-trivial solution of this system corresponding to each of the eigenvalues which are roots of the equation determinant of A minus lambda I equal to 0. When you have done that, then you have solved the matrix eigenvalue problem. So, let us consider a simple example by taking A to be a 3 by 3 matrix. Suppose say A is 2 0 1, 5 minus 1 2, minus 3 2 minus 5 by 4. I observe that A into x, which is 1 3 minus 4, is minus 2 times 1 3 minus 4. So, that this vector x, which has components 1 3 minus 4, satisfies the equation Ax is equal to lambda x. So, lambda equal to minus 2 is an eigenvalue of this matrix A. If x is an eigenvector associated with an eigenvalue lambda, so that Ax is equal to lambda x, then if I multiply this vector by say a constant c, then I have A into Cx is equal to lambda into Cx. So, if I call y to be Cx, then I observe that Ay equal to lambda y, and therefore, y is an eigenvector because it satisfies the equation Ay equal to lambda y. So, a constant multiple of an eigenvector of a matrix A associated with the eigenvalue lambda is also an eigenvector of the matrix A. Now, one can compute the eigenvalues and the corresponding eigenvectors by requiring that determinant of A minus lambda I equal to 0, but the computations will be very tedious when the order of the matrix is very large. And therefore, we require some numerical methods for computing the eigenvalues and eigenvectors of a given matrix A. So, we develop in this course a method known as power method, which computes numerically the most dominant eigenvalue of a given matrix A. So, you may ask me why only the most dominant eigenvalue and why not all the eigenvalues of a matrix. Of course, numerical methods are available for computing all the eigenvalues of a given matrix numerically for special classes of matrices. In this course, we focus only on the method where we are able to compute numerically the most dominant eigenvalue. The other methods which will help us to compute for special classes of matrices, all the eigenvalues are beyond the scope of this course, and so we focus only on the power method, which helps us to compute the most dominant eigenvalue. So, we describe power method now. Power method is used to compute numerically the most dominant eigenvalue of a given matrix. And it also helps us to obtain the corresponding eigenvector. So, the method is based on the following assumption, namely the matrix A has a single eigenvalue of maximum modulus. And that there is a linearly independent set of eigenvectors associated with the eigenvalues of the given matrix A. So, under this assumption we compute the most dominant eigenvalue of the given matrix. So, let us denote by lambda 1, lambda 2, etc., lambda n the eigenvalues of the given matrix A, and that they are distinct. And lambda 1 is greater than lambda 2 in absolute value, is greater than mod lambda 3 and so on, greater than mod lambda n. So, lambda 1 is the most dominant eigenvalue in magnitude. So, power method helps us to obtain this dominant eigenvalue numerically. So, if suppose I denote by V1, V2, etc., Vn the corresponding eigenvectors, what does that mean? It means A V1 is lambda 1 V1, A V2 is lambda 2 V2, or in general A Vi is lambda I Vi for I is equal to 1, 2, 3 up to n. Write down V, if V is any vector, then it is, I use an arrow above V to indicate that it is a vector, because we are solving a system Ax is equal to lambda x. So, x is a vector, if A is an n cross n matrix, X is an n cross 1 vector. So, associated with lambda equal to lambda I, if we determine xi, that xi is denoted by Vi, which is an eigenvector associated with the eigenvalue lambda I. So, it is a vector. So, any vector V can be expressed as a linear combination of the eigenvectors associated with the eigenvalues lambda 1, lambda 2, etc. So, any vector V will be of the form C1 V1 plus C2 V2 plus C3 V3 and so on plus Cn into Vn. And so, I compute A times vector V. So, C1 is a constant. So, it is A1, C1 into A V1 plus C2 A V2 plus C3 A V3 plus etc. plus Cn into A Vn. But what do we know about A V1? A V1 will be lambda 1 into V1. Why? V1 is an eigenvector associated with the eigenvalue lambda 1. So, I substitute for A V2 as lambda 2 V2, A V3 as lambda 3 V3 and so on, A Vn as lambda n Vn. And therefore, this will be equal to lambda 1 times C1 into V1 plus C2 into lambda 2 by lambda 1 into V2, C3 into lambda 3 by lambda 1 into V3 and so on plus Cn into lambda 1 by lambda 1 into Vn. And so, this will give me AV. Now, I consider A on AV, that is I pre-multiply both sides of this matrix equation by A. So, that will give me A square on V. So, that will be lambda 1 into C1 into AV1 plus C2 into lambda 2 by lambda 1 into AV2 plus C3 lambda 3 by lambda 1 into AV3 plus etc. plus Cn into lambda n by lambda 1 into AVn. So, I again make use of the fact that V1, V2, V3 are eigenvectors of matrix A associated with lambda 1, lambda 2, etc. lambda n. So, AV1 will be lambda 1 V1, then plus C2 into lambda 2 by lambda 1 into AV2 is lambda 2 V2 and so on plus Cn into lambda n by lambda 1 into AV1 is lambda n into Vn. And now I remove the factor lambda 1. So, I get lambda 1 square into C1 V1 plus C2 into lambda 2 by lambda 1 the whole square into V2. Because I have removed a factor lambda 1 from it, so this will be lambda 2 by lambda 1. I already have that factor, so it is lambda 2 by lambda 1 the whole square. So, I remove lambda 1 from this, that will give me lambda n by lambda 1 the whole square into vector Vn. Now, I see some pattern here, namely if I have A into V, that involves lambda 1 times C1 V1 plus C2 into lambda 2 by lambda 1 into V2 and so on Cn into lambda n by lambda 1 into Vn. If I have A square times vector V, then that is lambda 1 square into C1 V1 plus C2 into this plus etc. plus Cn into lambda n by lambda 1 the whole square into Vn. So, what do you think you will have when you compute A cubed V? That is going to be lambda 1 cubed into C1 V1 plus C2 into lambda 2 by lambda 1 the whole cubed into V2 plus etc. plus Cn into lambda n by lambda 1 the whole cubed into Vn. So, you can continue to obtain every time pre-multiplying the equation at this step by A and obtaining, say, at the nth step A to the power of n into V. So, suppose we do that, then A power n V is equal to lambda 1 power n into C1 into V1 plus C2 into lambda 2 by lambda 1 power n into V2 plus etc. plus Cn into lambda n by lambda 1 to the power of n into Vn. So, at the end of n steps we have A power n V to be given by lambda 1 power n into this sum of vectors. Let us apply it once again. What do? We pre-multiply this by A. So, we get A power n plus 1 into V and we pull out a factor lambda 1. So, that will be lambda 1 power n plus 1 into the sum of these vectors within the bracket. Now, let us take the limit as n tending to infinity. Then as n tends to infinity, we observe that the right hand side vector tends to lambda 1 power n C1 into V1. What happens to the rest of the terms? Lambda 2 by lambda 1 in absolute value is less than 1. So, as n tends to infinity of a quantity which is less than 1 is 0. So, all these terms tend to 0 as n tends to infinity, and the limit of A power n into V as n tends to infinity is lambda 1 power n into C1 into V1. Similarly, when I take the limit as n tends to infinity of A power n plus 1 into V, then I will have lambda 1 power n plus 1 into C1 into V1, and rest of the terms which appear within the bracket will all tend to 0, because we have lambda 2 by lambda 1 is less than 1 and lambda n by lambda 1 is less than 1 in absolute value. Now, let us look at this vector. What did we get? C1 V1 plus C2 into this plus etc. plus Cn into this. This vector tends to the vector C1 V1. Again, the reason being, in absolute value lambda I by lambda 1 is less than 1 for I is equal to 1, 2, 3 etc. n. So, as n tends to infinity, the vectors here are such that these terms will tend to 0 and we will end up with the vector C1 V1. So, this is the eigenvector associated with the eigenvalue lambda 1. Then how do you compute the eigenvalue lambda 1, which is the most dominant eigenvalue, and that is obtained as the ratio of the corresponding components of these two vectors, namely A power n plus 1 V by A to the power of n V. So, that is lambda 1 power n plus 1 by lambda 1 power n. So, that will give you lambda 1, and so lambda 1 will be equal to limit as n tending to infinity of A power k plus 1 into vector V by A power k into vector V, but take the mth component of each of these vectors, where m takes values 1, 2, 3 etc. up to n. What does it mean? Take the first component of this vector and take the first component of this vector and obtain the ratio of the first components of each of these vectors. And then similarly, work out the details by computing the ratios of the mth component of each of these vectors. Lambda 1 is given by limit as n tending to infinity of the mth component of the vector A power k plus 1 V by the mth component of the vector A power k V for m is equal to 1, 2, 3 up to n. When do we stop the iterations? We stop the iterations when the magnitudes of the differences between the ratios that we obtain turn out to be less than the given error tolerance, so that we obtain lambda 1 correct to the desired degree of accuracy, and the vector C1 V1 to which the sum of these vectors converge to as n tends to infinity will give us the corresponding eigenvector. So, let us take an example and understand power method, which helps us to determine numerically the largest eigenvalue in magnitude of a given matrix A. So, let us try to illustrate power method, which helps us to compute numerically largest in magnitude eigenvalue of a given matrix A. So, we need to control the round off errors in our computations. So, we take care of this by doing the following, namely we normalize the vector before multiplying by A. You just look back and see what we did. We at each step we pre-multiplied the vector v by A. Here we multiplied AV by A and so on. In order that we have control of round off error, before multiplying by A, we normalize the vector v. That is, we see to it that the largest element in that vector is unity. So, let v naught be a non-zero initial vector. We have to start with an initial vector v naught and generate a sequence of iterates for v, and which tends to the eigenvector associated with a given eigenvalue. So, we do this as follows. So, we take A v k and call it y k plus 1. Yes, we start with a vector v. So, A v is obtained, and that is what is mentioned here. Find at each step what y k plus 1 is. So, y k plus 1 will be A v k. And now, what is v k plus 1? V k plus 1 is y k plus 1 by m k plus 1. What is m k plus 1? It is the largest element in magnitude in the vector y k plus 1. So, compute A v k, call it as y k plus 1, remove the largest element in magnitude in that vector and divide y k plus 1 vector by m k plus 1 and call that as v k plus 1. So, if you pre-multiply now by A, you have a vector A v k plus 1, that will be your y k plus 2. From that vector you remove numerically the largest element, call it m k plus 2. So, divide your vector y k plus 2 by m k plus 2, and the resulting vector is v k plus 3. So, you continue to perform your computations this way. This will help you to control the round off errors. So, finally, what is lambda 1? Lambda 1 will be the ratio of the components, the mth component of vector y k plus 1 to the mth component of vector v k as k tends to infinity. And what is the eigenvector? Eigenvector will be v k plus 1, which is associated with the eigenvalue lambda 1 that you computed. In fact, you can see that as k tends to infinity, m k plus 1 gives you the eigenvalue lambda 1. So, choose your initial vector v naught with all its components to be equal to unity, provided you are not given any initial vector to start with in your computations. So, start with an initial vector v naught which has components 1, 1, 1, etc., and then compute a v naught, a square v naught, and so on, and take the limit as n tends to infinity to obtain the ratio of the mth component of these vectors in your computations, and that will give you the eigenvalue which is the most dominant eigenvalue of the given matrix A. And the corresponding eigenvector is given by vector vk plus 1 as k tends to infinity, and you have the required result at the end of your computation, namely the largest eigenvalue in magnitude and the corresponding eigenvector. So, we shall illustrate this method in the next class by taking some examples.